Good. Everyone can hear me well? Perfect. Okay, yeah. My name is Schneider. I started recently as postdoc in Chalmers. And as the picture already suggests, or the title already suggests, I'm talking now on the Dynamical Casimir Effect. And my idea is to prove the entanglement in the two photon bonds which come out pairwise. Now, in the background, what you see is, so it's an artwork by Philip, and this is an imagination. So you have a mirror, which you oscillate very fast in time. And what then happens is, at the mirror boundaries, photon pairs start to appear. And those continuously being generated, those photon pairs are expected to be entangled. And instead of a real mirror with a real mass, we have a circuit which actually is our equivalent circuit in the electromagnetic spectrum, where we have the Squid, which is displayed underneath, which is at the end of a transmission line. First, I want to give briefly the outline of this talk, so the motivation. I'm going to talk a bit about more of the Dynamical Casimir Effect, the Squid at the end of the transmission line, how do we calibrate it, and the conclusions. First, the motivation. What I find very interesting is, if we had a source for broadband entangled photons in the microwave regime, there are two types of applications which I find very interesting. One is quantum computing, and the other one is quantum detection. For quantum computing, you have this continuous variable quantum computing, and for this one you need entangled photons in many different frequencies. For quantum detection, sometimes your quantum detector is limited by the supply that you have in entangled photons. And for this, really like a broadband source of entangled photons is actually very interesting. But first about the Dynamical Casimir Effect, and why I think this is a very good source for such broadband entangled photons, is if you have a mirror here, which is this slab, and you oscillate this one very fast forward and backward at a frequency fp, where p indicates the pump of the drive, of the mirror, how fast you oscillate it, then you generate two photons, photon pairs, who add up to the same frequency as your pump frequency. And you don't get it just one photon pair. No, you get a photon flux density which is distributed as a parabola with a range of frequencies. And the intensity and how high this is corresponds to, or is proportional to, how fast you move your mirror. So the faster you move your mirror, and you can get maybe very close to the speed of light at some point, the more photons you generate. And those photons come out pairwise, and if you add up all the pairs and you look at the photon density, you get this parabola. And now the idea here is, I pick two frequencies which add up to the same frequency as my pump frequency, which is here at the end of the parabola, and look if these two frequencies, or the photons coming out there, are actually entangled. Now, how do I get a mirror that moves as fast as you expected? For this, I use a Squid, which is at the end of a transmission line. Of course, nothing is moving there. It's just a boundary condition where we have so the end of a transmission line is for microwave photons like a mirror for real photons. But now we have a Squid in front of it, and the Squid, what it does is it changes the inductance. And as it changes the inductance, exactly at the boundary of this mirror, you change the phase. And when you change the phase here, just in front, what happens is you have this, I don't know if this animation works, doesn't matter. So you have this, boundary condition which then depends on the flux which I apply to the Squid. And now this flux that I apply in the Squid, I can apply rather high frequency. And with using this method, you effective velocities of 0.25 times the speed of light has been achieved. And so what we're looking now onto is for such a device, I expect a photon flux density which comes out like a parabola, and if I look at the photons coming out at frequency f1 and frequency f2, I want to look at the two-mode squeezing, for example, or I want to calculate the log negativity and to prove the entanglement of these photons. Now, first, let me explain briefly one- and two-mode squeezing for those who don't know exactly what I mean with this. Because if you have an electromagnetic signal, you have a so I measure a voltage as a function of time. And this voltage, you have different points. You can separate it into two quadratures. It doesn't matter if you separate it into position and momentum, or in our case it's I and Q, or any other of these quadratures. But important is that if you don't have any squeezing in the system, you have a random noise in these two quadratures, and they are orthogonal to each other. If you just look at a signal which is just noise, then you would just get a circular shape where the diameter actually corresponds to the intensity of the noise that you're looking at. But if you now do have squeezing, then you actually convert noise from one quadrature into another. And then what you have is you find back a squeeze shape which is a bit like this. Now, this one is valid if I just look already just at one single frequency. Now, if I look at two frequencies, at frequency 1, F1, another one, F2, I can again separate the quadratures I1, I2, Q1, and Q2. And I can also compare those ones and can find squeezing in there. And if this squeezing is large enough, the two-mode squeezing, then you can actually compare it to the vacuum noise. But the thing for microwave photons, if you squeeze those, it doesn't mean immediately that it's entangled. You really have to actually compare how far below did you actually squeeze it. So did you squeeze your noise below the vacuum noise, or did you not? So what has been done and what is actually missing? So DC radiation two-mode squeezing. So DC radiation with two-mode squeezing itself has been measured. So here the measurement was basically just squeezing as a function of pump power in the flux. And flux, fast you modulate it, and the stronger the modulate it, the more photons you get. And here's a clear dependence in the amount of squeezing which goes up. Another experiment is here done with a Josephson metamaterial, where you have a Squid array which was inside of a cavity. And there, to some extent, squeezing and even entanglement was shown. Now the problem with these two things is the following. For the first one, there was a nice open transmission line, and there was clear squeezing, but one thing was missing. And that was actually comparing the amount of photons to the amount of noise from the zero-point fluctuation. For the second one, you have a very narrow bandwidth cavity, and inside of it you modulate your, let's say in optics you would have some parametric or some refractive index which you modulate very fast, and then you generate your photons. The problem is, for this one, it's very narrow bandwidth. What are we doing? So our device, we start with a simple sapphire wafer, we deposit niobium on top. Then we etch the niobium such that we define our ground plane and our coplanar waveguides. So on the left side we have our flux input, where we send in our current to modulate the flux in the squid. And over here we have an aluminum squid with aluminum junctions, which is at the end of a transmission line. So here is the ground plane, and there on this side, that's where we expect the DC photons coming out. Now, when they come out, we connect it to an amplifier, they get amplified, and later we split this up and we detect it into normal voltage detectors. Now, how do we first probe So the first thing what we do is we probe basically the reflection of this. So if I send down a signal in one line, goes through a circulator such that the signal goes in this direction down, passes the squid, sees the mirror, comes back up, and comes back out here where it is being detected. Now what we can do is we compare the phase between the signal that we send in and the signal which comes out. This is just for calibration. And we do that as a function of the DC flux that we change over here. And the DC flux corresponds to our mirror position, so that if I change the DC flux a little bit, my mirror position, or my equivalent mirror position changes. And what we see is a change in phase. And here we have 120 degrees, down there is 0 degrees, and this is basically what you get. Now, this is basically, again, where I have the mirror over here, and the electromagnetic waves see a different boundary condition. But how do we actually generate DC radiation? So for this, we tune the flux to a specific point. So our point of operation, we have a DC magnetic field, which we apply so that the squid is in a certain position. The blue curve here is now our phase, but what I calculated here is the effective displacement, where the phase corresponds to for this given frequency. And the other axis, or this other thing here, this is the reflection. This is basically how good is the reflection of your mirror. So how much of the signal do you get back? So over here you get nearly all of your signal back, but over here you have a dip. And this dip is because you hit 1/2 flux quanta and 1/2 flux quanta at the squid. That's where the critical current goes very close to 0. And so once we set the DC flux at this fixed position, such that we know that if I apply an AC signal on this point, I modulate this position forward and backward. So basically, what I'm doing is I'm setting a position, let's say 1.3 centimeters, and then I increase my flux drive, and that moves my mirror, or oscillates my mirror between 1.3 and 2.6 centimeters, such that I'm actually moving my mirror forward and backward. Now, this is basically the two things that you need to do. And the next thing is, you need to detect the signal. And so the DCE, or the DCE radiation, or the two photons, the photon pairs that I'm interested in, come out here, and I amplify them. So this is the first part where they're actually being detected. It's a Hemd amplifier. And then we split up the signal, and we detect them with 2 digitizers. Now, but how do we actually calibrate for the photon numbers? As I said before, we need to compare the squeezing that we have to the amount of vacuum noise which is in the system. So I need to know if I have 1 photon generated at my squid. So if 1 photon comes out here, then how many photons, or how much voltage does it correspond over here? Unfortunately, this plot doesn't work. So for this, I can do without this plot. That's fine. So for this, I have DC lines over here. So across the squid, I can apply a DC current. So this is a current source. This is a voltage measurement unit. So, and these black things indicate resistors. Typically, you want to have a large resistance to make sure that you don't add any noise from outside. So this whole system is at millikelvin temperatures. So this resistance is here, for example, are at 1 megaohm. If I want to apply 20 microamps, then I apply current, and I measure the voltage across the squid. And as I do this, I can measure what is basically the critical current of my squid. And I can also find what is the resistance of my squid. But what's better is I can also use this as a shot noise generator. So when I apply current which is larger than the critical current of the squid, I generate noise. And I know how much noise I generate. So I know basically I generate so much noise over here. So I can use this noise to calibrate my voltages over here. So from this I get I can fit. So I already converted this axis here, but I get actually a voltage on this axis. And then you can fit this to an equation, to the shot noise equation. From this, I get the gain, by how much I did amplify the system, and my noise temperature, by how much noise I'm adding just by having an amplifier there. And now if I look at the shot noise equation, I can convert this into my photon flux density by simply taking the voltage that I measured over here and divide this by the gain, the bandwidth, the frequency, and subtract the amplifier noise, which is added from this one. And then what's left over is basically the photons which are generated from this part, which I'm interested in. Now, if I do this, I sit at the critical current and I tune my flux to a fixed position, which is at 0.588 milliphi knot, or 588 milliphi knot. And I activate the flux pump. So I start shaking it forward and backward over here. And I increase this flux pump on this axis, and this is basically the units of milliphi knot. So I'm driving it relatively small still. And then I plot on the y-axis here, this is the photon flux density that I measure. And it starts with 0.5. 0-point fluctuations is usually with half a photon, if you have some noise. Then this one increases as I increase the flux pump. And this increase is basically the increase that I see also by photons are being generated, and I detect them. Now the next thing is, how do I actually prove entanglement of photons in DCE radiation? And for this, as I said, I need to compare to the 0-point fluctuation, or more specifically, what is actually the limit if I do not have entanglement involved? Because I want to show there's entanglement involved, so I need to know what is the limit if I do not have entanglement involved, and this is given by this equation, where you have the two frequencies, you have numbers of photons, N1 and N2, and then I compare, let's say, the cross quadratures from at the two frequencies, I1, I2, Q1, Q2. And from this I get a squeezing, and I compare this to this factor over here, which is a limit of how much I can squeeze if I do not have any entanglement involved. Now, I do this over here, where the x-axis, the y-axis here is the amount of squeezing calculated, which is basically how many photons do I have squeezing as in comparison to the total amount of photons. And you increase the flux pump, and the other axis over here, which is lower, this one is basically the limit of how far you can possibly squeeze if you do not have entanglement involved. And we were actually very conservative with these numbers, and the error bars are still quite large. But what we do find is there are few points, at least 3 points here, where there's possible entanglement, where I can say, okay, this is outside of the error bar, quite clear, and it's still both. And so what it means is that basically my squeezing is just below this, a little bit below the vacuum. Now, from this, what I can conclude is this is actually a promising broadband quantum entangler, but I didn't prove yet, at least from my feeling, I didn't prove yet fully the entanglement to a certain enough level. So I want to have more confidence, more data points, which I'm taking right now, to actually to be really 100% sure that that the photons which come out from this device are actually really entangled. So what else? We have a relative precise adjustment output power. And what's actually very promising about this one, the surrounding circuit, or the bandwidth, is actually just limited by the surrounding circuit. So you have your coplanar waveguide, you have your low-pass filters, high-pass filters, and that's about 4 to 8 gigahertz. And it's a relatively simple sample design, so it's very simple to implement and to do. Yeah.
So, first of all, So first of all, let me congratulate you on a very nice experimental program that you guys are developing. My question is, so if I think of it as an optics person, right? So I have nothing more than a fabric Barreau cavity. I have my phase that is oscillating precisely at the resonance. So then this squeezing is nothing more than a delayed response of the cavity, right? You're interacting with the resonance of the cavity in a linear sense, in a linear optical sense.
So squeezing you have if you convert noise, a noise quadrature from one to another. If you do it either because you interact with the cavity one way, or in optics, if you go that way, you have, let's say, a medium which is critically pumped, and you send down a signal, and at the moment where the photon intensity is larger than this critical value that you want, it converts this to let's say, phase noise, so that you know exactly the amplitude. Then basically you have an amplitude squeezed photon coming out.
So if you take your cavity and you set the Q of that cavity to 1, meaning free space, would you get any squeezing?
So this is a good question, but you have to interact somehow. You have to somehow interact with the wave which comes in. Yeah.
Another question. Let me ask you before, but
yes,
do my question. I don't see what type of squeezing of entanglement you are showing here, because one thing is to have two-mode squeezing, the other thing is to show entanglement.
Okay. So the entanglement here is in the I and Q quadratures. So the I and Q quadratures are undetermined until the moment where you measure them. So they're completely random at the moment where you measure them. In my case, it's at the moment where they hit the Hammond amplifier. So you get a photon which is entangled. It's another photon. And the moment where I measure this and I amplify it, that's where the entanglement collapses and you get, basically that's where I do my measurement.
I've got just two short questions. Can you go back one slide where you, if you look at this criterion down there, I mean, if I remember correctly, sort of all the quantum information theory, there are your continuous variable entanglement measures, based on variances of Q differences and I sums and so on and so forth. Is that related to what you've written down there? Or how do you come about? How does this expression
This one is
come
from
about?
this paper. This equation.
Oh, so I need to look at this one. Okay, fair enough. Sort of one small question is: how many photons do you actually get out as a photon flux? The number of photons per second. As a in terms of if you want to use that as a broadband entangled light source.
Yeah. So this.
How useful is that?
So this entirely depends how you actually use your system as well. But of course here the photon numbers are extremely small. But this is also because I'm a bit far away from where I have a large displacement factor. So I'm maybe not moving my mirror as fast as I can possibly do. So maybe I can move it faster so I can generate a lot more photons. This is what I'm trying to do, to get to a point where I reach to much faster effective displacement of my mirror, such that I can generate more photons and can be more confident on the entanglement being present.
So I had a question about what kind of figure of merit are you going to have? I mean, when you get a number out, how significant a number do you think you can extract from this? Amount of entanglement.
Okay, so there's one more method which I'm also using, which I didn't show here because of time, which is the log negativity. So this is basically the one that I also want to show. But I want to do this a bit more consistent and make sure that the log negativity is clear and obvious.
Hi. Hi Ben, thank you very much for the nice talk, and I like the setup you are building, and the results seem very promising. I have a very question which can sound perhaps a bit provocative. As you said very clearly, is when you have production of photons, it doesn't automatically mean that you have DCE. It must have also squeezing. And you also said that squeezing must be satisfy this criteria this criterion that you showed in your plot. So now the question is provocative in the sense the previous paper. Are you saying that they do not satisfy this criterion, or and therefore they didn't measure the DCE, or these two papers?
Okay. What I'm saying is they showed clearly DCE radiation, but they didn't prove that it was actually really entangled. So DCE, what we expect is that DCE radiation is entangled. That's what we theoretically expect. And what they have shown is that there was a very clear two-mode squeezing involved. And
this is the point. I mean, you can have radiation emitted, but it must be entangled in order to have a DCE, right?
But you can have also thermal photons in the system. So
correct. There will not be the
so
DCE.
then you wouldn't see the entanglement yet. The photons could be, I mean, the generated photon could be entangled. But because you have a seed of thermal radiation in there as well, you don't necessarily can observe it then. So
I agree. But the question, sorry if I repeat this, is therefore, with this criterion that you are considering, do they measure DCE? Do they measure entangled photons in there?
So for the criteria is for the entanglement in the DCE radiation.
For the entanglement in DCE radiation.
Yes.
They didn't test entanglement.
So who knows?
They take some.
So of course the data here is very promising in the sense that it looks like it's entangled. And in other aspects you do also expect that it will be entangled. It would be very surprising if it wasn't entangled. If I could prove it was not entangled, it would be even more interesting actually.